Assalamualaikum warahmatullahi wabarakatuh. And today, we will do an integrated project presentation. Our lecturer, Dr. Hamdan bin Muhammad Yusuf. So let me introduce our team. We are from Group 11. Our team member consists of me, Muhammad Aizal bin Muhammad Ibrahim, 1981-78, Nur Azliani binti Jamaluddin, 1986-81, Tarania, anak perempuan Balam Nurugan, 1966-67. Moving on. So, in table of content, so the first one is introduction, process description, recycle, sizing summary, comparison of aspirant and manual calculation, economic analysis, health and safety and environment, and also conclusion.
Hello Dr. Hamdan, I am Tarnia here. Now I am going to introduce about our project. Our goal of this project is to design a process for the manufacture of ethylene from shale gas with high purity ethylene production with 99.99% and its commercial significance in the world market. Ethylene is the largest of the olefin markets and is also most important petrochemically. And shale gas could also decrease energy costs because massive shale gas production will likely cause a significant decline in natural gas prices. If we compare with the other raw material, the shale gas we can get easily and it's more cheap than the other raw material. Capacity project. The production capacity of the plant is obtaining 99.9% of ethylene and the balance is ethane, which is undesired product. The regularity of this plant is assumed to be 99% and the number of operating days is 360 days per year. Annual production capacity is the approximately 167405.04 ton ethylene per year and price of ethylene for RM per ton is 7252.89. The operating prices is 213,456,295 ringgit per year. Okay, the facilities of the ethylene production include in ethylene production are the administrative and lab building, employee parking, and moreover, ethylene will be stored in non-pressurized storage tank. Ethylene is used in the range of industries and applications including the production of chemical, food, beverage, glass, medical, metal fabrication, and moreover, the largest regional use of ethane occurs in US and Canada. Now I am going to explain about the process description. Okay. This is our block flow diagram. First, our raw material, which is a shale gas, will enter the pressure reduction unit and then will enter heater. Then our OCM reactor. So the OCM reactor then will enter to the cooler. So in OCM reactor, we have three input, which is the oxygen from ASU, which is supply oxygen to reactor, and then the recycle stream from the distillation column. Okay, so and then the separator will separate the methane, and next separator is separate methane also, but it collect a more purity methane and send back to the reactor. Finally, we can obtain our purity ethylene 99% at a final separator. This is our process flow diagram. Okay, units. Now I am going to explain about the valve. The pressure from 11 bar is dropped to 6 bar when the temperature is slightly decreased from 26 degrees Celsius to 23.7 degrees Celsius. The mole flow rate is and out is same because the purpose of this unit just to reduce the pressure at input. Okay, and the same goes to the heater. The heater is device designed to heat the vapor from to 3.7 degrees Celsius to 8 to 5 degrees Celsius, and the pressure is still same, that is at 26 bar. The purpose of using heater at this stage to heat up the flow so rate, the separation process at the OCM reactor will be easy. The OCM reactor conversion of ethane is 25%, where the conversion of carbon dioxide is 100%. So the yield of ethane is 0.21 and selectivity of to ethylene is 67.4. So our ASU is achieved to separate the oxygen from air and supply it to OCM reactor. And the temperature is 98 degrees Celsius and pressure at 6 bar. Cooler. So first cooler, we have two coolers. So first cooler is to cool the substance because temperature is at 3 degrees Celsius and 6 bar is pressure. The second cooler, the substance must be cooled before entering the demethanizer, which is operate at 41 degrees Celsius. Okay, and the amine absorber is actually to eliminate the carbon dioxide from the system. The 99% of carbon has been eliminated from the process. The C2 splitter is we use in distillation as our model of distillation, which is number of stages 118 and number of fifth stages 62 and reflux ratio is 1:2. So the higher reflux ratio can cause a higher purity of the distillate. This unit operate at 8.516 degrees Celsius at pressure 35 bar. Recycle and purge. Recycle stream function reduce the purchase of fresh reactant because the stream is required into OCM reactor. Okay, and the heater again is last sector is enter the heater to increase the temperature to 85 degrees Celsius. This is because it will enter OCM reactor which operates in 85 degrees Celsius. Okay, that's all from me. Thank you, doctor.
So my name is Nur Azlani, so I'll continue on in the recycle stream summary. So this is the recycle stream that we propose, which is from the distillation column. This is because a lot of byproduct from the methanizer, which is methane and the other like components, so we want it to be recycled, and the recycle stream therefore will mix with the feed, original feed, and will enter the OCM reactor. So before that we have the recycle stream and purging stream. So from the demethanizer, the stream will split into two streams, which is 50% of it with the same temperature and pressure will goes into heater and OCM reactor, while the other half will be purged. Purging is necessary to remove an accumulation of unwanted material and to prevent buildup and overload in the reactor after recycle. So this is a comparison in OCM reactor between the product stream with a recycle and without recycle. So in the presence of the recycle stream, so we can see here the total mole flow rate of the stream with recycle is increased from 2200 to 2800. This is because in the recycle stream there is ethylene and ethane. Therefore, in the outlet stream of OCM, we can see the increase in flow rate of the ethylene and ethane and also the methane. Next is the production of ethylene after recycle. So when this is the first recycle, so we can see that it is increased from 16,000 to 21,000. So when the recycle process is repeated over and over, there will be increase in production of ethylene at the end.
Okay, so today for my part, I would like to explain a little bit about the sizing summary in our project. We can divide it into a few parts, which is the distillation column stages, column and plate sizing, and also plate efficiency. So in distillation column stages, we'll be doing the binary in our. We'll forget to mention that in this project we'll be focusing on the distillation column. So for our design, we are using the binary distillation. And also in this distillation column stages, we will talk about the TXY diagram. And okay, so for the column sizing, we will calculate the column diameter and also the plate thickness of the column. And finally, for the plate efficiency, we will talk about the efficiency of the plate and some of the other calculation. So moving on to the distillation column sizes. So this is the TXY diagram for ethylene ethane system at 1 bar. So this is temperature versus mole fraction of ethylene in liquid and vapor. So this basically we are using the Excel based on the manual calculation we made and Excel. So we will get this thing. And also for the assumptions we made, we got 3 here. The boiler is in equilibrium. The relative volatility is constant. The molar overflow is constant. By doing the McCabe-Thiele method, we can calculate the stages of our distillation in this diagram. Since our distillation is a binary, and this is our stages, we got like 5.4 something stages. And this is for binary distillation. So for mixture, it will be different type of calculation. Moving on. So in this stages or calculation of stages, we will be using like Rawls law, P equal to Px, where P is the partial pressure of ethylene in vapor, Pa is pressure of pure ethylene, and Xa is mole fraction of ethylene in liquid. And also end-to-end equation, as always, this is our most important equation. Log P equal to A minus B over C plus T. P is vapor pressure, AB constant, and T is average temperature. Our average temperature is 106.8. And for the relative volatility, we can get the composition of the vapor of ethylene. So this is the relative volatility that I will show you how do we get this next. Okay, so this is the ABC, constant for ethylene and ethane. We got this value from Google, and this is all the value. This is based on, the temperature is based on Kelvin. So after we got the ABC, we can calculate the P set using the atomic equation, and it will get the value respectively. So the temperature is 106.81. So we're using the average temperature of the dew point plus the boiling point. So this is the relative volatility that I talked about. This is the value is 4.5393, and molecular weight of ethylene and ethane is displayed here. So moving on to the next one is about the provisional plan design is to be considered. So we calculate the column diameter, column area, downcomer area, net area, active area, whole area, take 10%, fraction of downcoming, fraction of whole area. So this is all the values that are for the variables here. Also, we will check whipping of the column by doing the maximum liquid rate, minimum liquid rate, which is 70% turn down, maximum HOW, H the maximum HOW is going on. So to calculate the design minimum velocity, we will be using the UH. So this to calculate the minimum velocity. So to get that, we need to K2. So based on this figure here, wet point correlation, we can get the K2 here. And then the K2 will be get is 28.5. So we will get the equation, the value, we will get 235.0129. So for the actual minimum velocity, we just 70% of it times this, and that's the minimum. And also next on is we can also calculate the residual head based on the equation below. HR equal to 12.5 times 10 to the power of 3 over PL. So PL is the density of liquid. So the value obtained is going to be 19.73 millimeter liquid. So we make assumption of the original, which is 100 millimeter. So total pressure, total plate pressure drop will be calculated based on the HD plus bracket real length plus maximum HOW, close bracket plus HR residual head, and the formula. So that's the formula. The value for the final gonna be 2204.98 mm liquid. So finally, for the next part of for this column and sizing, will be made assumption of the area of the hole, which is 0.01964 meters square, and in the end around 27 hole is obtained. So moving on to the plate efficiency. For plate efficiency, we get two table here, two figure here. The first one is for PL and the second one is for PV. So PL is for basically the liquid one, which the bottom composition taken, and the PV is for the top composition taken. So this is the total mass of the bottom, and this is the total volume and relative density. So for ethane and ethylene, mass fraction is based on the Excel calculation. Also respective mass that we get from here, which is the total mass. The molecular weight of the ethane and ethylene, the mole of the ethane and ethylene, mole fraction of ethane and ethylene, respective volume, the density of ethane and ethylene, actually we calculate this in Excel calculation, the respective viscosity, ethane and ethylene, W over U, respective viscosity and relative molecular mass. So next one is the for PV. It is the same type of table as PL. The total mass is the different one. This one is the top composition, which is for vapor, and you can see here that the total mass is bigger than the liquid there. So the total volume for ethane and ethylene is all displayed here. So finally, for the plate efficiency here, we can see that before we calculating the plate efficiency 42.4%, we actually calculate about like a few variable, which is the diffusivity of liquid, a factor, molecular mass of A and B, summation of diffusion volume constant. So basically this is all in the book. The step is the same as in the book. We just follow it, and this is the final plate efficiency we get.
So next is the comparison between Aspen and manual calculation. So for this part, I'll only explain on several parts that give a significant effect on the overall process in this plant. So the first unit is aspiration unit, which a huge difference have been made here, which is in our manual calculation, the inlet is only 152.5 kilogram per hour, while in Aspen simulation we put it as 91,000 because the inlet flow rate that we use here is too low for enough oxygen supply for combustion process in OCM. So the increase of feed here will give an effect to the overall ethylene production at the end of the process. So next is the OCM reactor, which from the Aspen simulation, we know that we have made some changes here. So there are increase in ethylene composition from the changes that have been made. So the other component is also increased because of the outlet stream flow rate is also increased. So next is the carbon dioxide removal. So in manual calculation, there are two parts in this unit, which is the first part is amine absorber and the second part is amine regenerator, which we are using MEA as the solvent. So in Aspen simulation, we only use the absorber to remove the carbon dioxide. And there's more removal of carbon dioxide in Aspen simulation because we use the high efficiency of absorber to remove the carbon dioxide, which around 95%. So next is for the metanizer, which in manual calculation the assumption that have been made is all methane and light component is fully recycled. But in Aspen simulation, the assumption for methane purity is 97%, and also the recovery is 97%. Hence, a small amount of methane and other like component is also will enter the cytosplitter. So, from the ASU that have been made some changes, it result in different flow rate and composition of these two uh, from the manual calculation and the Aspen simulation. So lastly, this is our last unit, which is cytosplitter. So in manual calculation, we only obtain 99.1% purity of ethylene, while in Aspen simulation, we obtain 99.59%. And in Aspen, we assume the recovery of ethylene is 99%. So there is some increment in this priority because the feed of the cytosplitter in Aspen simulation is higher than in a manual calculation. Therefore, it increases the priority of this cytosplitter and the ethylene.
So for the next part, I will talk about economic analysis. So for economic analysis, we can separate it into a few parts, which is the equipment cost, capital cost, operating cost, and cash flow analysis. So for the first part, economic cost. In our design of this project, production of ethylene, we use a few units, a major unit and a minor unit here. For the first unit, we got is OCM reactor. So the price is huge. The price is expensive because it's a reactor. And this is the price. Distillation column, heater, cooler, pressure relief valve, air separation unit, compressors, splitters, separators, and also amine CO2 removal. So this is all the price per unit. So as we see here, there's some unit that repeated, like heater, cooler, and distillation column, because our design need to use them like a few more to make it more good. So this is total cost, which is 388,878 ringgit. So moving on to the capital cost. So the capital cost, basically the the cost of the plant they are ready to start up, which is to represent the capital necessary for install process equipment that fully furnished with all the components that are needed for system to operate. So this is the freight and transport, 5% of total TEC. So this is the value. The equipment of cost at site, TEC plus FNT, length factor for solid 3.89, ISBL cost, total ECF. So this is the value, OSBL cost, 40% SBL, total SBL or SBL, design and engineered DAE, contingency, total fixed capital cost, estimating work capital, and also total investment required. This is all the value. So basically this is the step here is actually taking it from the journal. So moving on to the operating cost. So each of our unit need to operate by year. So operational of this unit, our operation, gonna take 330 days per year, and it's operate 24 hours. So this is a heat exchanger, process reduction. We got use power here, and also electricity cost. And this is all the equipment we are using, and some of them using power here, and some are using reaction. So this is the total of the electricity cost here per ringgit, and this is the production rate of ethylene. So moving on to the operating cost. So as we know, $1 equal to 4.18 ringgit. So we can calculate the variable project, which is the raw material and utilities. So this is the raw material. We use MEA and water here. So this is the kg per hour we are using. This is the kg per hour, and this is the ton per hour. So the cost that we are using. And for electricity, we got 800 to 1 kilowatt. So this value we will talk about later a few after this. How do we get this value? So the total is this one. So fixed cost, capital cost, before this we calculate it. So labor plus plant overhead and laboratory 20% of the operating cost. So this is the final one we got, like 553 million. Okay, so variable operating cost, raw material. So for raw material we got amine and also our feed, shale gas. And so this is the cost feed, which is amine is 1,250 USD per ton, shale gas is 80 USD per barrel. And this amine and shale gas is really big here, as you can see, total mass and the cost here per year. This is all per year. So same to ethylene, tariff of the water will be based on the IS website here. You can see here that 2.07 ringgit per meter cube. Moving on to the electricity, and the industrial tariff for the electricity is 0.327 kilowatt per hour. And this is obtained from TNB's pricing and tariff website. So the price is actually constant throughout the whole period of production. So this is below here is the tariff for the TNB. Okay, so for the final part is cash flow analysis. So in this project, the production plant operates 24 hours a day and 333 days a year. So there will be some risk analysis evaluated based on the highest and lowest price of our feed and product. So our feed is shale gas and amine. So the highest price will be this one, and the lowest price will be this one for shale gas. And amine will be constant for highest price and lowest price. So for shale gas, the total mass is this one, and the total highest price for the shale gas ringgit Malaysia per year will be this one and this one. This one is for the highest and this one is for the lowest. Amine here also will be the same for amine, and this is for total price for amine. Total price for amine per ton, this one is per year. So for product, which is ethylene, the highest price will be 725.2.9, and the lowest price will be 2828.3. So this is the total mass, and this is the total highest price and the lowest price of ethylene. So this is the graph of the cumulative cash flow. This is diagram. So it's good to illustrate the performance of the project, and it's the cumulative cash flow, over the life of the project. So the annual cash flow correlate to the money that were invested and money that were gained. In other words, it's different between the profit and also the loss. So to summarize this, the profit will by subtracting the total operating cost from the sales of methanol production. So the project investment is approximately like 214.2 million. To illustrate this, so our company Complexity will support a huge money of investment for the chemical process and also successfully synthesis ethylene from shale gas. So for health, safety and environment, so in an industrial petrochemical gas, ethylene produced in the large quantity worldwide. So ethylene manufactured of the best well-controlled high temperature thermal cracking OCM reactor using ethane, methane and oxygen as feedstock. So it's highly flammable and explosive, so it will be protected from the contact with direct heat or flames. Ethylene is manufactured in a closed equipment system for safe handling and processing. So exposure for ethylene at workplace or risk to environment is strictly controlled in our country. So okay, so since 2004, the industry have adopted occupational exposure limit for ethylene of less than 200 parts per million. It's also highly volatile and not expected to remain in water or on the soil surface. Lifetime ethylene in atmosphere between 0.4 to 4 days. average of 1.5 days and depend on the amount of the sunlight. So as the conclusion for this project, we want to convert the shale gas into ethylene by obtaining 99 purity of the ethylene. So for production of ethylene, major equipment will be used for the reaction to occur. So for the ethylene, the plant design, total production for the 99% purity is this one. And also the raw material, which is shale gas and amine, is this one, the total per year. And the equipment cost, and also the investment, our investment that I said before. So about our product, this one is supposed to be highest price and this one to be lowest price. So it is about to produce a detailed design since preparatory design has given acceptable return on investment. So upcoming project, a lot of improvement can be made with proper planning for ethylene production. So this project really contributes a lot of knowledge to us